Okay, so again, good afternoon, everyone. Welcome to APNIC eLearning web class. Today is the 7th of February in 2018. It's 3 p.m. in Brisbane, Australia, where I'm doing this class. And this is the last session that we're doing for the day. So normally we conduct 3 sessions, each of which runs for about an hour. So it can go beyond that or just stick to the 1 hour, usually depending on how interactive the class is. So if you do have any questions at any point in time, I would like this class to be interactive. So if you have anything to add as well, please feel free to write them down on the chat. Now, I don't usually allow audio coming from participants. So if you have any comment, please just use the chat panel to do so. All right, so what are we going to talk to today? It's about IPSec VPN Design. So essentially, this is an introduction to the concepts behind IPsec and how it operates, and what are the different components that we need to understand to, because like configuring IPsec, especially on 2 devices that are the same, usually can be quite easy. But understanding the concept behind it and how it works and what are the protocols and RFCs that cover it is something that we also need to understand for troubleshooting purposes. So before we go through that, my name again is Sheryl Hermoso. I'm a network operations engineer at APNIC. I also do a lot of these training, and I do conduct different topics, particularly network security, IPv6, DNS and DNSSEC, and Internet Resource Management. Now, again, this class runs for 1 hour, and at the end, I'll be asking you to fill in a survey. So please just take a couple of minutes to complete that survey. The link I will be posting at the end of the session. All right, so what our focus is today is on VPN, particularly on IPsec. So I just have a very minute introduction of what VPN is. I'm pretty sure most of us knows about that, but just an introduction to IPsec. And then we'll jump into the concepts of IPsec, the benefits, the different modes, tunnel versus transport mode, and when to use each one. What are the different components of IPsec that completes its entire architecture? And lastly, some examples on how you can set up IPsec VPN tunnels. I have an example for Cisco. The commands are all in the slides that you can quickly just follow if this is something that you are going to do. All right, so first off, just a brief introduction of VPN. What is a VPN? We all know what VPN is. It's it's a protocol that allows you to have secure communications, secure channel in between endpoints, in between 2 networks that can be logically or physically away from each other and passing through a physical network or public network, right? So it allows us to have that secure communication even though, okay, it goes through a public channel, which a lot of like thousands of other people use. There are many types of implementation of VPNs. It can be in between networks. It can be clients to network, client to firewall. It can be in between firewalls or between networks. We use the VPN. The VPN uses the public internet as the main backbone. Therefore, allowing us to easily set it up anywhere and everywhere as long as you have internet connection. It can have different forms as well. VPN using IPsec is just one of them. There are many ways to do it, different technologies like using SSL. There can be using like a GRE tunnels. You can have a combination of different components or different protocols too. Or generally, there are 2 types of VPNs, remote access VPN and site-to-site VPN. So that relates to the first bullet point there, where you have client to firewall. So essentially, it's between, say, one machine going to a network. So if you're working remotely, if you're working from home, that is your machine or your computer, having a software or select some commands that you can implement to connect to your VPN server onto your, let's say, company network. Now, site-to-site VPN usually something that is like kind of like in between networks only. So regardless of users, they don't really have to worry too much about it. Anyway, if you have your microphones on, if you can please mute it, or I can disable it from here as well, just so it doesn't affect all the other folks in the room. So I've done that for, okay, I've done that now, so we can continue. All right, so that's VPN, but particularly we wanted to focus on IPsec, right? So why IPsec and why would you choose IPsec? Let's try to understand that. VPN for most parts are implemented either on layer 2, layer 3, or sometimes in some cases on the upper layers like layer 7 application or transport as well, like or the SSL version, SSL protocol part. But IPsec works on layer 3. Now, there are a few advantages to doing this. It's because it is applied on a lower layer. It's something that network operators, network administrators do, but is mostly um, like users don't have to be affected by it. Most applications don't have to be compatible with it. Okay, they don't need to set up anything. Okay, you don't have the special configurations on the client side. So it's kind of like beyond the users. So only on layer 3. So it's transparent to applications and there is no need to have any IPsec integration, so to speak. There is on your routers, there is on the network devices that you're going to use, but not on the application side. Now, IPsec is actually a set of protocols and algorithms. There are some reasons why a lot of folks are discouraged about IPsec, and that's partly this. It's a set of different protocols. It's in some cases a lot of things to take in. You have these different components: security associations, authentication headers, encapsulating security payloads, and internet key exchange. So in by themselves actually are quite big if you look at the RFCs. So the RFCs are the standards that define these components. So you have a lot of these that like specifications that looks at each of these components and how they work together. Um, so yeah, it's a set of these protocols and algorithms used to secure IP data, again, at the network layer side. It's also a security context for the VPN tunnel, and it's established via the ISAKMP. So aside from those four components, we have your ISAKMP, which is a key management protocol, which you will find useful. Well, normally don't have to do much about it because it's automatically created. But if you choose to have or manage your like keys manually, it's possible. But instead, normally you rely on a key management protocol such as this. I'll show you some of that example. IKE is actually one example of that. So yeah, a few more things about IPsec here. It's an IETF standard that enables encrypted communication between peers. So again, it's normally used between networks. It's an open standard and it scales from very small to very large networks. So home networks, if you want, you can always set up like IPsec. A lot of like small routers do have support for IPsec already. Usually it's just like one page or one configuration that you tick. In some cases, even the information that you have to add can also be defaulted to something, especially if it's between same devices. So yeah, it can work on small networks, but very large networks also usually rely on IPsec, particularly for telcos and operators who has many clients, corporate networks that are like part of their their ISPs that they serve. So it can cater for very large networks. These are the IPsec standards that you have to be familiar with when you talk about IPsec. Actually, this list is already the updated or the new iteration. I think the initial RFCs, if you want to see the very first ones, is like 2300 series. So first one is the IP security architecture, how it's all defined, how the architecture plays together and the different components work alongside each other. So different elements that are used are also defined here. Now you also have, you mentioned in the previous slide that the two components are AH and ESP. So there is an RFC that covers each one, RFC 4302 for AH and RFC 4303 for ESP, or Encapsulated Security Payload. ISAKMP is RFC 2408, IKE. Now there are two versions of IKE that you will see later on, IKE version 1 and IKE version 2. IKE version 2 is RFC 5996. And then the last RFC there is a list of and an explanation of the cryptographic algorithms that can be used and supported by ESP and AH. Alright, so I keep mentioning about those components. We'll take a closer look at each one. But for now, what are the benefits of IPsec? Why would you go for it? Of course, you have all the benefits that VPN gives you. But more specifically, it gives us the three, I guess, the goals of security. What are you trying to achieve? Of course, with IPsec, we can achieve confidentiality. And how do we do that? By encrypting your data. Of course, that's the main goal of having a VPN anyway. Like, you want your data to be secure. You want your data to be encrypted so that it can pass through a public network. And that is easily done in IPsec. The next one is integrity. Where does integrity play here? It's when you are, of course, you communicate one-to-one, client to server, or server to server, router to router, is that right? So each of those routers are configured to communicate or create a channel only in between those two devices. And through IPsec, okay, one of the features of IPsec is, of course, it is able to check the integrity of the other router, other device that is communicating with. So each end of the tunnel has a checksum or hash value, and they're able to verify that the data that they receive is correct and that they are talking, indeed, they're exchanging data between the right parties. The last one in this list is authentication. So it's all about signatures and certificates, right? So how do you, well, of course, how do you exchange data? You have to be able to authenticate with that machine, either remote device to the machine or router to router, same thing. You should be able to verify and authenticate that that machine can actually send data in that regard. So this is also done in IPsec via authentication, right? So actually, IPsec was designed initially to be part of IPsec. It's part of, of IPv6. It's part of the IPv6 specification. If you hear people saying that, oh, IPv6 is more secure because, well, it is like the specification says so. Part of the reason for that is because of IPsec. So IPsec is a concept originally evolving from like when they are creating the specifications for IPv6. However, it's taking us a long time to actually all migrate to IPv6. So of course, we needed some form of protection, I would say, right? Some security on layer 3, right? Because right now, what sort of like security do you provide on layer 3? Usually it depends on the protocols that are operating on that layer, right? So like the routing protocols have their own like kind of like security in mind. So IPsec is something that can provide that sort of protection as well. So it's designed to provide interoperability, high quality and cryptographically based security for both IPv4 and IPv6. So in IPv6, it's part of the protocol. In IPv4, which was of course standardized way before IPsec was conceptualized, so IPsec is another protocol. So you kind of like see both protocols interacting or operating at the same time. But with IPv6, it's already part of the protocol. So that's kind of like the main difference between them. All right, a few more benefits. I guess the first bullet point here is something that we've already discussed, data signing and also signature verification. It's all part of that. But I also wanted to just point out anti-replay protection. What is this? So replay attack is, it's a kind of attack wherein someone can do a man-in-the-middle, MITM attack. So you sit in the middle of two devices that are talking to each other, grabs the data, grabs the information, and then reinserts it back into the network. So the other party, let's say B, when he receives the packet, he still thinks that he's communicating directly to the previous device, so let's say A and B. So he thinks it's still communicating with A, whereas actually the data has already been modified or altered by the attacker. So it's kind of like, that's like the term came in because like it's replaying. So the data has already been sent, okay? He's like capture the data and then replay it back into the same link at a later time, most likely modified, or if not, there's just like some delay. So it affects how the other party operates. It can be related to keys, or it can just be like raw data that is being passed. So it has kind of like that effect, of course, on the network or in the communication. But with anti-replay protection, IPsec is able to easily check or verify that it has already received the data previously. Therefore, if it has, this packet that has been resent, most likely from an attacker, so like it's a doubtful, it's doubtful like whether it came from an attacker or not. So it will just be dropped because he's already received that. So it's just like part of the packet itself. There is, you will see in the header, there is a field there that has a value that is used for anti-replay protection. And the last one in this slide is key management. So I've mentioned earlier that you can manage keys manually in IPsec, but usually you don't really do that. So IKE, Internet Key Exchange, and also eSAKMP Key Management Protocol is being used for this purpose. So you have to establish sessions in IPsec, and usually it's not just one session. These sessions also expire at some point. Keys has to be continuously created and expired, so there needs to be a proper key management, and IPsec does that pretty well. Right? So just to be sure before moving forward, this is where we are with IPsec. Again, the application layer is usually not affected most of the time, of course, but all the trouble, all the work, all the configuration is done in between the routers in this diagram, so it is in the network layer, right? And everything that's beyond this link layer are all now encrypted. All right, so any questions so far? Okay, so that's just like an introduction, of course, of what IPsec is, so to give us a bit of an overview. Now let's go into more details. There are two modes in which IPsec operates, and this is something that usually you would notice. By default, it uses tunnel mode, okay? Most of the routers, let's say Cisco routers, would probably use tunnel mode by default, but you always have options to switch between these two modes. But what's the difference between the two, and which one do you use for which case? So let's look at each one. The first is tunnel mode. With tunnel mode, it is frequently used. Let's look at the use case first, right? So it is frequently used in an IPsec site-to-site VPN. So remember earlier I told you that there are usually two types of VPN, remote access and site-to-site. So this one is for site-to-site. So if you're configuring it in between two networks, you would normally use tunnel mode. And just quickly go to transport mode. When is it used? It's frequently used for remote access VPN. So client to server, client to router model usually would be using transport mode. Okay, so configuration wise, usually it's just a matter of choosing which mode you're going, but operation wise, it's a bit different. So tunnel mode, the entire IP address, or sorry, IP packet is encrypted and becomes the data component of a new and larger IP packet. Now, I'll let you take some time to digest that. So you have a packet, this entire packet is encrypted, and then it becomes a data component when it is passed through. How does that actually work? Let's look at this quite quickly. The diagram on top is, well, your typical packet, right? It doesn't have IPsec or anything at all. So in a typical packet, you have an IP header. So this is layer 3. Remember, this is layer 3. So you have an IP header and an IP payload. So this whole thing from your TCP header all the way to this end is your IP payload. Now you know that the IP is coming from the TCP, like the layer above. So this, in this case, TCP. So that is meaning you have a TCP header and your TCP data or TCP segment data, right? So this is basically your entire IP packet that comes in on layer 3. Now when you're operating on tunnel mode, look at the one at the very bottom. So tunnel mode IPsec, remember this is your actual packet, IP header, TCP header, and payload. That's this one here, right? So IP header, TCP header, and payload. That's your original packet. Now, it will be now encapsulated in your IPsec, right? It will be encapsulated with IPsec. Therefore, there will be a new IPsec header. You can see that here. The orange box is an IPsec header. And then it's followed shortly by a new IP header. Now, why is there a need for a new IP header? It's because you have now encapsulated the original IP header. And for this to be read on layer 3, you need a new IP header. Right? So yeah, here you have a new IP header. So what's the effect of this? You now have a much larger packet than you originally have. See, your original packet is this. Now you have an extra IPsec header and an extra IP header. How big is a typical IP header? Right? In IPv4, that's 20 bytes at least, and it can also increase. So that's again already an extra 20 to 40 bytes. So it can be a problem to your network if you have very low values set that is allowed to go out of your routers, right? Okay, the next one is transport mode. Let me just go back here quickly so that we can see the definition. So transport mode IPsec header is inserted into the IP packet. So you see, no new IP header is created at this stage, unlike in tunnel mode. Okay, so I'm going back to the diagram again. It's this second one. So what happens is somewhere in between your original IP header and your original IP payload, okay, you're just splitting them into two and inserting a new IPsec header. So that's kind of like the main difference between them, I suppose. It has an implication on which parts are encrypted, which ones are not, which ones are exposed, but it's not to say the transport mode is lesser than tunnel mode. It has its own purpose. It has its own use cases where it is mostly used, right? So yeah, but like implementation wise, notice the difference between these two is that how the IPsec header encapsulates the payload or the whole packet. And then, like, of course, as a result, you either have a new header or just using the original header. When is it implemented? If you are doing transport mode, okay, notice the orange dotted lines. So it's between the two machines that are talking to each other. So it's end-to-end communication. Whereas with tunnel mode, you start tunnel mode once it reaches the router. So the blue dotted lines here, okay, specifies only in between the routers, only in between the gateways. So traffic from here to here may be encrypted in another way, okay, but the with IPsec, it will be from the router all the way to the router. Whereas if you have a remote access VPN, for example, that's using transport mode, the encryption begins with the machine that you're using, right, in the end system. Okay, so that's one of the main difference between them as well. All right. Okay, just going back here quickly. So what does that mean when you have to have a new IPsec header? So when it is here, like when your packet is created here, when you have a new IPsec header, okay, notice that the source and destination IP has changed. So let's say, for example, my packet is coming from this machine, machine A. Okay, there's no name there, but like let's just call it machine A. It's coming from here. What's the source address? It's A's IP address. What's the destination? It's B's address, right? However, when it reaches this router and I have IPsec configured here, the source and destination will now be this router, and the destination is of course the other router on the other end. So the new IP header will have their IP addresses the original IP address will be part of the IP header that is encapsulated. Therefore, once it's received on this side, let's say B's network, B's router, once it's received here, it will be the encapsulated, right? So you'll have the original packet, which still has the IP address of machine B. So it still can get to the destination. Okay, so yeah, that's how it works. All right, any questions? No questions? All right, moving on to the IPsec architecture. I've mentioned these components earlier. You have AH, ESP, IKE. You'll say, oh, there's so many terminologies that you have to be aware of. Now, yes, there is apparently, but it's something that you can get used to after a while. But the important bits would be that AH and ESP are the security protocols. Normally, you can implement only AH or only ESP, but in some cases, some people also do AH plus ESP. Okay, you'll see the difference between them in the next slide. IKE is Internet Key Exchange, which establishes the tunnel, and it's also in charge of key management. So you'll see phases of IKE. So when you look at the process of exchanging packets or setting up the tunnel between two routers, that's actually done using IKE. So how does it all work? How does it all glue together? First of all, you have an IPsec security policy. Security policy is, of course, based on your own security policy as a company, right? For example, you're saying that, oh, these are the only protocols, encryption algorithms, and length of keys or hashes that we support in this company. That should also translate to your IPsec security policy. That means that if you are going to communicate with, say, other networks in establishing your VPN connectivity, okay, you'll have to have only support for these encryption algorithms, these hashing algorithms, and the number of keys, something like that. Right? So normally you have a set of security policies. Okay, you want your best security policy at the very top. Let's say, for example, you are supporting DSA or maybe RSA. Okay, let's say, for example, you want to support DSA, which is the current standard for public key cryptography. For hashing, you want to support SHA-256, right? 256 bits using secure hash algorithm. Okay, and then of course the key will be 256 bits or maybe longer, depends on your policy. So that is your priority, I guess, priority policy. I don't know if there's a term for that, but basically that's the top of your list, so that when it negotiates, you'll see that there's a lot of negotiating happening between two routers in this case. So when it negotiates, it will try to say that, hey, this is the protocols that I support. Do you also support this? Okay, and then the other party will of course check, and if they don't, okay, they come back to you and say, oh, okay, sorry, we don't really support 256 bits, maybe 128, or we don't support DSA, we only support RSA. So usually that's the part like where you have, that's why you have many, like you have other options, like the minimum that you accept, for example, is RSA using 128 bits, for example, so SHA-1. Okay, so you can do that. So that's your secondary option. But then if you don't have a policy for, let's say, I don't want to accept MD, message digest. So you don't have that. So if the other party only supports message digest for the hashing algorithms, then no connection, okay, no tunnel will be formed between these two because they have not agreed with the policies. Okay, so that's usually a high level view of what the security policies do for you. Now related to that is security association. So SA is a collection of parameters required to establish a secure session. Okay, so you can say that when I described in the previous slide how they establish that connection, they actually use these parameters. And these parameters are saved in what we call as security associations. So they exchange security association to see whether the other party supports it or not. Okay, so security associations have three parameters that are uniquely used to identify them. SPI, so basically it's just like an index, a unique number that identifies an SA. The destination IP address has to be unique, and of course, what security protocol you're using. Are you using AH, are you using ESP, or using both? An SA can be either unidirectional or bidirectional. Okay, if it's in, so again, you'll see this in the next slide, but there are two phases in IKE. You have the phase 1, which is, you can see here, is an IKE phase, which has IKE security associations. This one is bidirectional. So during the first phase, it's bidirectional. During the second phase, however, which is your IPsec phase, you have IPsec security associations there, and this one is unidirectional. What does that mean? You'll need two security associations for a bidirectional communication. So when you're establishing connection, you'll need two security associations. And usually, if you want both AH and ESP, it will have two for each. So you'll have 4 or 2 sets of security associations to use both AH and ESP. Right? So that's security associations. ISAKMP, as I've said, is Internet Security Association and Key Management Protocol. Okay? Guess, as I've said, the only thing that as a beginner you have to understand here is its use. It's a framework that is used for key exchange and key management. So it supports, or it uses, like the particular protocol under ISAKMP is IKE, which is Internet Key Exchange, and Curverized Internet Negotiation of Keys. Now, both of these are mostly supported by a lot of devices, but I guess by default, most people would just use Internet Key Exchange. So this one is the more popular one. So that's what we're going to describe in a short while. Next one, security protocols. We said that we have two, right? I've already mentioned them a couple of times. Authentication header, or AH, and the other one is ESP. So let's just discuss them together. What's the difference between them? So this is the security protocol. So this is where you decide what type of security you want to achieve. Is it confidentiality? Is it integrity? Right? Is it authentication? So with AH, it provides you with 2 out of those 3 goals. That means you have integrity, you have authentication. Okay? But what's missing here is the C, right? Where is confidentiality? So you use this if your goal is to protect your network from spoofing, of course, from replay attacks and things like that, but you're not really worried about providing confidentiality in the link. That's all good if that is your purpose. Now, it operates on top of IP. It uses protocol 51. Okay, so I'll show you some examples in a bit. But what's the difference between that and ESP? So ESP provides all that AH is offering, plus extra data confidentiality. So it gives you that encryption. It supports encryption. Okay, it does that by using mostly symmetric key encryption for encrypting your data. Okay, for establishing the connection, it uses public key cryptography, but when the channel is already established and you're actually sending data between 2 parties, then it's using symmetric key algorithms. All right, so that's I guess the more important bit here is to understand which one is used where. And in this case, if your focus is on confidentiality, then you provide ESP. If your focus is on data integrity, then you use AH. There are many times when people do use both. Why? Because this one is arguable, and they said that the authentication part of AH, the way it's implemented, is better than ESP. And so to get the best of both worlds, they would have AH plus ESP. Okay, so it is up to you which one you use. Most of the time, it is supported in a lot of devices. Questions so far? Okay, so now let's merge the two together. We've talked about AH and ESP, which are the security protocols. We've talked about the different modes, 2 modes to be exact, transport and tunnel mode. Now let's look at your header, how it expands when you're using either, like a combination of them. So for this one, it's AH in transport mode. Authentication header does not provide any confidentiality, remember? So AH header is used for authentication only. So basically, you're adding this AH header in the middle because this is transport mode. Transport mode is splitting the original header and the payload and inserting the header, the authentication header, somewhere in between. So what does it do? It provides a way to authenticate this part of your data, okay, except for mutable fields in your IP header. So that is transport mode AH. How about transport mode ESP? With ESP, you're providing confidentiality. Therefore, you need to know which part is encrypted. It's confidential, right? With AH, everything is authenticated up to the last part, up to the end of your data. Whereas here, okay, with your ESP header, right, again, this whole IP header from your ESP header all the way to, well, a trailer, of course, should be inserted only between the original header and the original data. So in that case, you're inserting this ESP header, and then you are adding an ESP trailer and ESP authentication at the end to signify up to where is the part that is encrypted, right? And the authentication bit is to tell you what the authentication data that can be used for your verification. So that's how it is. Like, see how it is already expanded. You have bigger files, bigger packet in ESP than in AH already, like when looking at this. How about in tunnel mode? How does it affect? Now, this is very similar to the previous two slides, but of course, now you're creating a new IP header and you're adding the AH header and encrypts the whole data, including the original IP header, right? That is the purpose behind it. So you can see that this is your original header, it goes through here, and then this is your AH header, right? And then you have a new IP header. So again, the increase in the amount of the size of your packet is obvious here as well. Whereas if you have tunnel mode, sorry, that's tunnel mode as well. If you have ESP and tunnel mode, okay, again, you'll need some ESP trailer to signify the encrypted part and your ESP encryption as well. So kind of like, yes, this one is a much larger packet than your, say, AH in transport mode. Okay, so hopefully this one is clear, just like giving you some idea on how tunnel and transport mode works and how it affects either, like if you choose AH or ESP. All right, next part is we'll go through the process of creating the IKE, okay, or creating the tunnel itself. So I've said IKE is used for establishing IPsec sessions. Now again, we have modes here. Okay, not to be confused with tunnel versus transport mode. We've gone through that. I hope that you already understand that. Now, just with IKE, we have different modes. You have two modes, particularly you have main mode and aggressive mode. There's a third one, but that is for the second phase. But let's go through this first, right? All right. These are actually the three modes here, just like a list of like what they are and some description of these modes. Again, you have two phases in IPsec, phase 1 and phase 2. We're talking about IKE version 1, which has two phases, right? In phase 1, you have options to use either main mode or aggressive mode. The default is main mode. You have the option to use aggressive mode at the expense of losing some functionalities. Okay? Again, so what is it and how does it work? Quick mode, I'll just describe in a little bit, right? That's basically similar to what main mode and aggressive mode will do, but for phase 2. So phase 1 for the time being, main mode versus aggressive mode. Okay, so with phase 1, okay, how do we establish network here, or the links between two routers here? It's using public key cryptography. In phase 2, we'll be using private key cryptography. This is how it works, okay? Phase 1 first, and then you will have a secure communications channel after that, when then it enters into phase 2. So that means, okay, that phase 2, which establishes an IPsec tunnel, is actually created inside phase 1, okay? So first of all, you have two routers, you create a channel in between them. That's the end of phase 1. After that, you create a tunnel inside that communications channel. Establish an IPsec tunnel. That's your phase 2. Once you have phase 2 completed, that's the time that they are able to exchange traffic in a secure way. Okay? All right. Now let's focus a little bit on IKE phase 1, but using main mode. Okay? Main mode negotiates eSEC SA to create the IPsec security associations, and it is done using 3 steps. So they're actually exchanging 6 packets or 6 messages to each other. Each step requires backwards and forwards, so 2 messages per each step. The first one is negotiating the security associations. After they have agreed on that, they will do a Diffie-Hellman exchange. And then the last part is when they authenticate each other, provide authenticated information as well, and then establish the secure channel. All right, let's go through the diagram to explain that a bit more. It's a bit like this, okay? You have 2 routers trying to connect to each other. We call the first one as the initiator. We call the other one as the responder. Okay, initiator, responder. These are just like mainly like whoever starts the conversation, initiates the conversation, sends the first message is your initiator. Okay, and then the responder gives answers or responses. How does that work? So first of all, your initiator sends the first message. That is your proposal. So remember security associations? Security associations are collections of parameters that you support based on your security policy. So let's say you propose that, hey, let's use this algorithm, let's use these parameters for our connection. Okay, that's the SA proposal. You're sending that to the responder. The responder will check whether in his own security policy he has that as well. He supports that as well. And then if they do agree, that is when the other party responds with the message 2. Now this can go on a few times. Okay, 2 is a minimum, but it can go a few times if they don't both, at the very beginning, they don't both support it. Okay, so meaning maybe default for the responder is a bit different than what you have, and then somewhere down on your list, like less priority of supported parameters, that's when you meet, that's the time that you have completed this step. But at this stage, of course, let's just assume that the very first try, it's accepted with the SA that you originally proposed. So that completes the negotiation phase. That's step 1. Step 2, are these values pre-configured on both sides or can be negotiated automatically from one side? Well, this is where the policy comes in, right? When you configure, you normally you manually configure your parameters. I guess that's the part that you set up. So it's not really, I'm not sure like what values you're referring to here, but the proposals like in the SA is usually configured per router. Okay, something that you specify, like that's something that's based on your policy. So it can be the same with the other party, or maybe you both like you're both managing these two, so you'll end up having the same at the end of the day. But it's something that you configure initially per router. Okay, I might have that in the example that you can see later on. The other question is about the materials in the slide. I'll post the link where you can download the PDF copy of these slides later. Once towards the end, let me just like take some time to grab the link for you, and then I can put it on the chat panel. Okay. So going back to Pierre, I hope that answers your question. All right, so yeah, we can have a look at the one later on if I have it here, because this is a trimmed down version of the typical IPsec materials that I use, but yeah, I should have that towards the end. All right, so phase 2 is Diffie-Hellman key exchange. How many of you are familiar with Diffie-Hellman? Public key cryptography, you know, there are many algorithms that fall under this category. One of them is Diffie-Hellman. The purpose of public key cryptography is that you have two keys, right? One public and one private. Diffie-Hellman is a public key cryptography, okay, that is used only for key exchange. Okay, it's not used for anything else. Usually, you don't use it for what you typically use for RSA or DSA. No, usually it's just for exchanging keys, not for encrypting anything. But how does it work? It uses very high values, very high random values. And through the Diffie-Hellman algorithm, they are able to exchange or to come up with the same value. All right, so they are public parts, so they come up with very high value of, or very high digit, and then they exchange that publicly. So let's say P and Q, and then once it's exchanged, of course, that's public. Anyone can read that. However, those two will go through an algorithm wherein they're able to come up with a value that is the same, okay, that is based on the original data that they exchange. And then that's a time that they are now going to use symmetric algorithm, right? So again, the purpose of Diffie-Hellman is to, at the end of the day, to come up with the same value or same key that they can use for subsequent encryption. So up to this part, you have public key cryptography. Once you have that common key between them, you switch to symmetric algorithm, right? So that's Diffie-Hellman key exchange. So the first part from the initiator to the responder is just like telling them the public values. This is the P. This one going back is actually the Q, and then they do the algorithm. And then the last stage, or the last step, the three-step process, is the IKE peer identity, right? So you've only provided confidentiality here. You still have to authenticate the other parties. Okay, you have to provide authentication mechanisms for that. So authentication materials, nonsense, and key IDs and stuff like that will be provided back and forth here to fully establish phase one. This is only phase one, okay? This is only phase one. You already exchanged at least 6 messages between them. However, this last part, the third exchange, is already encrypted. So only the first 2 are totally public. The last 2 messages, or the last step, is actually fully encrypted already. Questions so far? All right, so how do we achieve this using aggressive mode? So main mode, 6 steps, aggressive mode, 3 steps. Okay, that's half. But what are the, what are the things that you are letting go of when you do this? So these are the things. It has no denial of service protection. It does not have any identity protection. It can have exchange, but it's optional and it's not widely implemented. So again, I guess the end of the day, the purpose is to achieve that secure channel, right? And that is achievable using aggressive mode, using only 3 messages. But again, it's you don't have DOS protection, you don't have identity protection. By default, however, main mode is used. So if you're okay with it, you can always just stick with using main mode. Questions? All right, I can see someone typing. Okay, I'll wait for that to finish. But for now, let me go through IKE phase 2. So phase 1 is finished, right? You have either main mode or aggressive mode. At the end of either one of those modes, you have a secure channel. Phase 1 is completed, done. Next phase is phase 2, which is using quick mode. We only have one option, one mode here, only quick mode. At this stage, you're kind of repeating the same steps. You're negotiating, exchanging nonces, exchanging authentication materials with each other, but all this is happening inside your secure channel. Okay? Each quick mode negotiation results in 2 IPsec security associations. Remember that? I mentioned earlier that you have 2, you need inbound and outbound security associations, okay, to complete the full exchange. So that's you can achieve that here easily. Okay, so that is where you establish phase 2. Won't go through the detail here because the idea is pretty much the same. right? So these are the steps. You have the key materials, and then accept, and then send the proof identity, authentication materials, etc. And then that's it. By the end of this, okay, all that computation done, you now have an IPsec tunnel. Let me just go back quickly so that we can all see. Okay, it's actually a few slides back. So at the end of those two phases, you have this. Okay, you have here, you can now exchange secure traffic at the end. Okay, questions? All right, there seems to be no questions there, but okay. I told you at the very beginning, I hope you still remember that there are actually two versions of IKE. IKE version 1, which is what we just discussed, and then there's another one called IKE version 2. You got it right, IKE version 2. So why do you have IKE version 2? There's some people who are not exactly happy with the way IKE version 1 is implemented. It's the documents, the RFCs, and the implementation is always mostly different from each provider, from each vendor. Maybe it's partly because there's so many things and so many suppose specifications added on those documents that it's up to interpretation a lot, and there are so many additional features that were added later on to it. So it's kind of like become bulky and stuff like that. So you will notice that some of the complaints with IPsec is actually when you're using different vendors, different devices. If you're using Cisco, or Juniper, or whatever firewall you're using, these firewall devices, usually the setup is easy because everything is the same. The configuration is the same, the naming convention is the same. But if you look at two vendors, sometimes even the naming convention of how they call like security associations or the modes may be different. So it's hard to connect them, and you get a lot of like issues or errors and things like that. That's how IKE version 2 came to be. Okay, so with IKE version 2, they've added a lot of things. They've improved the documentation a lot, improved the way the specification works. Okay, it's still using IKE version 1 as its baseline and copies most of the features and characteristics from it. But the extra extensions that were later on added were actually not part of the original IKE version 1 specification. So it's like additional RFCs, right? So with this, they also combined those extra features and extensions. One of that is related to authentication that was used for, say, trying to remember. I'm not sure if I have that here. No, it's not there. But yeah, it's related to authentication. Say if you're using older protocols that are not really supported in IKE version 1, it's like part of the extension. Now it's added here. I can't remember the details for now. Sorry about that. But yes, and also some features were later on added to it. Now, question is, how does IKE version 2 work? It's so much simpler. IKE SA init is the negotiation, kind of like similar to the first set of message that we sent out, the SA proposal and SA accepted part. So that's this, exactly this. Okay, IKE SA init. So two messages at least. It can be more like in the IKE version 1 if they have to negotiate a few times. But then after that, okay, during the authentication, you also create two messages. Usually, just after these two messages, you can already have your what do you call it? Your tunnel. The tunnel is already done. Okay. These ones, these are secondary ones. Okay, child SA. So usually after the IKE auth, you have one child SA, and then you now have a secure channel. You now have your IPsec tunnel is already formed, and then they can exchange data after that. Okay, of course, it's not as simple as this. We have to go through the details, but at the very least, you'll have two, four, five messages, or six if you want to like count both ends, but like at least five messages, and you already have IPsec done, compared to two phases, six and another six messages each for each phase. So it's kind of like a bit more complicated. This is much more simple than IKE version 1. Unfortunately, we won't go through the details of each one here. Um, um, there are still a lot of devices that focuses mainly or supports only IKE version 1. So if you're going to implement IKE version 2, it is backwards compatible, but you'll have to check whether it's easy to do so. Now, for the configuration part, as I promised, these are some, well, I have some examples of how it's configured. These are the commands that you normally use. This example, by the way, uses Cisco. Fortunately, I don't have other devices to set up for this, so we only have Cisco examples. So first step, configure IKE phase 1 policy, right? Step 2, set the ESAKMP identity. What is this for? You're pretty much just identifying which machines or which devices are talking to each other. Step 3 is configure the IPsec transfer set. This one provides you information about the crypto algorithms, the security associations that are used between them, and also the mode. Are you using tunnel? Are you using transport mode, etc.? Okay, so three-step process. But like step 5, sorry, there's a step 5 and 6 actually. You have to create the crypto map. So that's where you identify who will be the peer, the IP address of the peer, which transforms that you're using, okay, which security associations are going to be used, pretty much using the previous information from step 1 to 3. And then the last part, which is also equally important, is you have to apply the policy to an interface. Let's look at this example here. Okay, this is the router configuration that I have. So it's actually easy and straightforward. You have just a few lines here, and also some here. But at the end of this session, by looking at this configuration, I hope that you can identify and see, all right, this is the part where we are doing phase one, and this is the part we're doing, we're identifying the things or the parameters that we're using for phase two. For phase one, that's the crypto eSEC policy here. This policy is just like a policy name. We call it eSEC policy 1. And then we identify the authentication, encryption algorithm, the hashing algorithm, and the Diffie-Hellman key exchange group that we're using here. Okay. For authentication, we're using pre-shared key, pre-share. That means we have to provide the key for symmetric, like symmetric algorithm, like symmetric key that we're using here. Encryption, we're using AES. As you know, AES is a symmetric algorithm, right? So that's the preferred over DES or triple DES. So AES is what we're using. For hashing algorithm, we're using secure hash, SHA. Okay, other option for this is if you have message digest or MD. But of course, SHA is better and more secure than message digest as of this moment. And then Diffie-Hellman key exchange, there are a few numbers like that define like the level that you wanted to use. Group 5 is very typical, so we use group 5 here. And then here, crypto ISAKMP key. This training 1, 2, 3 is the pre-shared key. And then address, to which IP address or to which remote device you are going to have this IPsec VPN set up for. In this case, it's 172.11.66. Okay. Now, next one is crypto IPsec transform set. This part, ESP, AES, SHA, is just a name. This can be any name. But this one, ASP, AES, and SHA HMAC, is where you define the encryption algorithm and authentication mechanism that you're going to use. Okay? In our case, we're using ESP, AES, and SHA with HMAC for our authentication. Next part is you create your crypto map. This is like step 5, right? Create your crypto map. We're naming it Lab VPN. Match address 101. You'll see that in the next slide. Set transform set. This transform set that we defined. Set peer, the IP address of our peer. Okay, that's pretty much it that you needed there. The access list that we defined previously here, match address 101, is this access list. Access list 101, permit IP. So this is between two networks, 172.16.16/24 and 172.16.20/24, right? So you're defining the interesting traffic by creating this ACL. And then you have to apply that onto an interface. In this case, let's say your outgoing interface from router 1 is FA0/1, so you apply that on that outbound interface. So CryptoMap Lab VPN is applied into int FA0/1. So what does that tell us? What can you gauge from this one? The important part, I suppose, would be defining the interesting traffic. Let's just say you have this VPN set up between router 1 and router 2. Okay? If you have different traffic there, if you define this, all the other traffic that goes through there going for different destinations or coming from different sources will still be transported, right? It will still be passed along between these two routers. It will still be forwarded, but it will not use your tunnel, your VPN tunnel. Only if your packet, okay, is using any IP within the range for this source and any IP for this destination, okay, will it be using your VPN. All right, does that make sense? That's the reason why this part is also important. You don't just define this part, okay, you define the security associations and the authentication mechanism. You don't just do that. You have to apply that to an outbound interface for your interesting traffic. All right? Does that answer anyone's questions from earlier? Okay, so I hope this one is clear. If you have any more questions, I don't think I have any more slides here. There you go. All right, there is one question there. Is there a way for a second device to retrieve all the config values by just entering the destination IP address and correct pre-shared key? Now this part actually that depends on the device that you're configuring it with. Usually there are default values. Usually, let's say if particularly if it's not pre-shared key, okay, there are default values that you set per device or per router. You might have to input 1 or 2, but I haven't seen one, to be honest. I always have to configure something, even just the key. You'll have to configure at least one.